Hello everyone, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself Jaimin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 1, which is a phase equilibria. So let's quickly revise what we have studied in previous lecture. In previous lecture, discussed about the quantitative behavior of vapor-liquid equilibrium. To understand the quantitative behavior of vapor-liquid equilibrium, there are mainly three diagrams: TXY diagram, PXY diagram, and PT diagram. PT diagram, which also known as a retrograde condensation. So, in TXY diagram, T stands for the temperature, X stands for the particular component mole fraction in liquid phase, where Y stands for the mole fraction of particular component in vapor phase. So now in this lecture we are going to discuss about simple model for vapor liquid equilibrium, such as for the Raoult's law and for the Henry's law. So let's first discuss about the simple model for vapor liquid equilibrium. When thermodynamics is applied to vapor liquid equilibrium, the main goal is to find out by the calculation the temperature, pressure and composition of phase in a equilibrium. Indeed, the thermodynamic provides the mechanical framework for the systematic correlation, extension, generation, evaluation, interpretation of data. Moreover, it is meant by which prediction of various theory of molecular physics and statistical mechanics may be applied to practical purpose. None of this can be complete without model for the behavior of system in vapor liquid equilibrium. The two simplest models are Raoult's law and Henry's law. Raoult's law that can be given by the YIP is equal to XIPI saturated, where Henry's law that can be given by YI into P is equal to XI HI, where Pi is a vapor pressure that can be replaced by the Henry's constant in Henry's law. Raoult's law is mostly used for the ideal solution, where Henry's law used for the dilute solution. So let us discuss in detail about the Raoult's law. This figure shows a vessel in which vapor mixture and liquid solution coexist in vapor liquid equilibrium. If vapor phase is assumed to be its ideal gas state and liquid phase is assumed to be a ideal solution, then we can apply Raoult's law for the solution and calculate the mole fraction in vapor phase and liquid phase. Mathematical expression for the Raoult's law that can be given by YIP is equal to XIPI saturated, where YI is a mole fraction of component I in vapor phase, where Xi is a mole fraction of component I in liquid phase, where P is a total pressure and Pi saturated is saturated pressure, or can say that vapor pressure, where I is a particular component 1, 2, 3 or n. So there is various limitation for the Raoult's law. We cannot apply Raoult's law for the real solution or dilute solution, or we cannot get correct data for the real solution using Raoult's law. So we can only use Raoult's law for the ideal solution or ideal mixture. Second limitation for the Raoult's law is that we cannot apply Raoult's law for the critical temperature or above the critical temperature. We can only use Raoult's law for the below critical temperature system. Next limitation for the Raoult's law is that we cannot use Raoult's law without knowing vapor pressure of particular component. So if we want to use the Raoult's law, we must have to know about the vapor pressure of particular component. So these all are various limitations of Raoult's law. Raoult's law can also use for the calculation of dew point and bubble point. Dew point calculation and bubble point calculation. So Raoult's law can use for the dew point calculation and bubble point calculation. So let's first discuss about the bubble point calculation. Let's consider there will be a binary system for the route flow binary system, which means there will be a two component. So if we are going to apply route flow for component 1, then that can be given by y1 p is equal to x1 p1 saturated. Now this is a calculation for dew point, so x y1 plus y2 becomes 1. So if we are going to apply the route flow for component 2, then it becomes y2p is equal to x2p2 saturated. Now we know that y1 plus y2 is equal to 1. So if we want to rearrange this equation number 1 and this equation number 2, we will get for the equation number 1, y1 is equal to x1 p1 saturated upon p, and y2 is equal to x2 p2 saturated upon p. Now using this value of y1 and y2 in this equation number 5, we will get y1 plus y2 is equal to x1 p1 saturated upon p plus x2 p2 saturated upon p is equal to 1. So by rearranging this equation, we will get, taking this p to this side, so we will get x1 p1 saturated plus x2 p2 saturated is equal to p for this binary system. So this is the equation for the dew point calculation with route flow. This y1 plus y2 becomes 1. That's why this equation becomes like this. This equation is a route flow for bubble point calculation for the binary system. Now if we want to apply this route flow for the multi-component system, then that can be given by p is equal to summation of xi pi saturated. So this is the equation for the particular component to find out total pressure from bubble point calculation using route flow. So what we done here, first take the binary system which means two component system. So applying route flow for the component 1, that can be given by y1 p is equal to x1 into p1 saturated, which becomes our equation number 1. Then applying route flow for component 2, that can be given by y2 into p is equal to x2 p2 saturated, which becomes our equation number 2. Now rearranging this equation 1 and 2 by subjecting y1 and y2. For the equation number 1, if we are going to subject the y1, then it becomes x1 into p1 saturated upon p, and if we are going for the component 2, that becomes y2 is equal to x2 into p2 upon p, which becomes our equation number 4. Now we know that for the bubble point calculation, we have to use y1 plus y2 is equal to 1. So if we are going to use y1 plus y2, then we have to put the value of this y1 and y2 from using this equation 3 and 4 in this equation number 5. So if we are going to use the value of this y1 and y2 in this equation, we will get equation like this. Now rearranging this equation, because we know that y1 plus y2 is equal to 1, so replacing this y1 plus y2 is equal to 1, so this equation becomes x1 p1 saturated upon p plus x2 p2 saturated upon p is equal to 1. By taking this p common to this side, we will get the x1 into p1 saturated plus x2 into p2 saturated is equal to p. Now if we are going to apply for the multi-component system, then this equation can written like this: p is equal to summation of xi pi saturated. So now let's discuss about dew point calculation. To derive equation for the dew point calculation, let's first consider binary system. Binary system, which means which made of two component, component 1 and component 2. So let's again apply route flow for component 1. So if we are going to apply route flow for component 1, then it becomes y1 p is equal to x1 p1 saturated. and for the component 2, that can be given by Y2P is equal to X2P2 saturated. Now, making subject of x1 and x2, this equation number 1 and this equation number 2 becomes x1 is equal to y1 p upon pi saturated. Similarly, for the equation number 2, which becomes x2 is equal to y2p upon p2s. Now, we know that x1 plus x2, which becomes 1. So, using this equation 3 and this equation 4, in this equation number 5, we will get y1 p upon pi saturated plus y2 p upon p2 saturated is equal to 1. Now, rearranging this equation, we will get p is equal to 1 upon y1 upon p1 saturated plus y2 upon p2 saturated. So this becomes our dew point calculation equation using the Raoult law for the binary system. Now, if we want to use the Raoult law for the multi-component system, then it becomes P is equal to 1 upon yi upon pi and summation of this whole term. So this becomes P is equal to 1 upon summation of yi upon pi saturated. So it becomes dew point calculation using Raoult law for the particular component. So for dew point calculation, first consider binary system which made of component 1 and component 2. Applying Raoult law for component 1, that becomes y1p is equal to x1p1 saturated. For component 2, it becomes y2p x2p2 saturated. Now subjecting x1 and x2, because there is a bubble point calculation, so we have to consider x1 plus x2 is equal to 1. That's why we are taking the x1 and x2 as a subject. So x1 is equal to y1 into p upon p1 saturated and x2 is equal to y2p upon p2 saturated. Now using this equation number 3 and 4, in this equation number 5, we will get equation like this. Now rearranging this equation, taking p common and taking to this side, so it becomes p. So this equation becomes 1 upon yi pi saturated plus yi p2 saturated. So this equation becomes p is equal to 1 upon y1 p1 saturated plus y2 p2 saturated for the binary system. Now if we are going to apply for the multi-component system, we have to summation of the all components. So we have to summation of this all components. So we are going to add sigma at this step. So this equation becomes p is equal to 1 upon summation of yi pi saturated. Now let's discuss about the Henry's law. Henry's law states that partially pressure of species in vapor phase is directly proportional to liquid phase mole fraction. So equation for that given by yip is equal to xi hi, where hi is a Henry's constant. So for the Raoult law, this equation given by yip is equal to xi pi saturated. So this pi is replaced by the hi. Raoult law is used for the ideal solution, where Henry's law used for the dilute solution. So let's suppose this is a beaker and there is a water in this beaker. Now we are going to pass ammonia from this water. Now some ammonia will be absorbed in this water. Now if we want to measure mole fraction of this ammonia in this water, we cannot use Raoult law, because Raoult law is only used for the ideal solution. Now if we want to measure the composition of ammonia in this water, then we have to use Henry's law, because some portion of ammonia is absorbed in this water, and if we want to measure how much ammonia absorbed in this water, then we have to use Henry's law. Henry's constant, that can be given by hi, and the unit of Henry's constant is the same as a pressure. So this is the various example for the Henry's constant. So this is all about the Henry's law. So in this lecture, discuss about the simple model for liquid equilibrium. There are mainly two models for the vapor liquid equilibrium, such as a Raoult's flow and Henry's flow. Then discuss about the Raoult's flow and their limitation and their application. Then derive the equation for the dew point calculation with Raoult's flow, that can be given by P is equal to summation of Xi Pi saturated, and then derive the equation for the bubble point calculation using Raoult's flow. So these both equations are useful for calculation of mole fraction in liquid and mole fraction in vapor for particular component. Then discuss about the Henry's flow. Henry's flow which used for the dilute solution. So this is all about today's lecture. I am completing my lecture here. Thank you.